Jain to everyone. In this lecture, I am going to discuss about the waveguide. This lecture is this topic is related to the 7th sem subject microwave and radar engineering, that is KEC 074. So in this lecture, I am going to discuss about the waveguides. In the previous lecture, I have discussed about transmission line. So in the transmission line, I have told you that basically the transmission line can be classified on the basis of their geometrical and electrical specifications. So in the geometrical specification, multi-conductor and single conductor can be used as a transmission line. In multi-conductor, coaxial cable, twin lead line and parallel plates can be used, and in single conductor we are using only the waveguides. So in the electrical mode, we can use TEM mode or non-TEM mode. So in non-TEM mode, that is TE mode, TM mode and HEM mode, etc. So this has been already discussed by me. What is transmission line? In transmission line, what is TEM mode? In TEM, basically TEM mode is a mode of propagation characterized by the electric field and magnetic field patterns that are purely transverse with respect to each other and with the axis of the transmission line or the direction of propagation. And this transmission line can support TEM mode on only if there are at least two disjoint conductors in its cross section and the medium filling in the cross section is the homogeneous, isotropic and lossless. So this has been already discussed. What is TE mode, TM mode and hybrid mode. TE mode is basically transverse electric mode, and transverse electric mode electric waves are also called H waves, and these are characterized by the fact that the electric vector being always perpendicular to the direction of propagation. In TE wave, only the electric field is purely transverse to the direction of propagation and the magnetic field is not purely transverse in nature. And in TM mode, transverse magnetic waves, also known as E waves, are characterized by the fact that the magnetic vector is always perpendicular to the direction of propagation. In TE wave, only the H field is purely transverse to the direction of the propagation and the electric field is not purely transverse. That is, Ez is not equal to 0 and Hz is equal to 0 in case of TM mode, but in case of TE mode, Ez is equal to 0 and Hz is not equal to 0. And in hybrid mode, both TE and TM waves are coupled together and are present simultaneously. In other words, we can say that both Ez and Hz are non-zero. Ez and Hz is not equal to 0. Sometimes in hybrid mode, the EH is known as HE or EH mode. So these are the modes of transmission line which can be defined, and how can we define the TE mode, TM mode and hybrid mode. Now what is the appropriate model? This has been already discussed by me that in lower that how will we make a model using the transmission line. In a mathematical model gives us the cutoff frequency and propagation constant for the transmission line. For low frequency, we will use lumped element model, and for high frequency we will use the field model, and for medium frequency we will use the distributive element model. But the transmission line is generally a few wavelengths long, then it is convenient to extend the lumped element model into the distributed element model. So in distributed element model, the transmission line is assumed to be made up of a series of lumped element or distributed element model where V and I cannot vary over each incremental length delta Z. So here I have considered the transmission line which is having a length of delta Z. Here the lumped equivalent you can say that this is the lumped model, or you can say distributive model. Here I have used the lumped series element in this distributed model. So here I have used the resistance, inductance, capacitance, and impedance. Here you can see that the R and L are connected in series, where G and C are connected in the parallel. So these are the R, L, G and C are known as the primary constant, and basically units are same as here I have considered this R, L, G and C per unit length, and this can be, here I have considered that the length of the transmission line is delta Z. Here if the input is Vz, input voltage is Vz and the current is Iz. So at distance delta Z, what will be the value of this current? Iz plus delta Z and Vz plus delta Z. So here you can see that the R is multiplied by delta Z, L is multiplied by delta Z, G is multiplied by delta Z and C is multiplied by delta Z. So here I have considered that the resistance per unit length, R is the resistance per unit length. For delta Z distance, I have considered the value of resistance will be R multiplied by the distance delta Z. So that will be the value of the resistance for a particular length of the transmission line. So we can find the propagation constant and the characteristic impedance using this distributive model. So we can write the equation from the previous model. Vz plus delta Z minus Vz divided by this, Vz divided by distance is equal to minus Ri minus L delta I by delta T. So Ri is for the distance Z. So I have written here the equation, generalized equation, V delta Vz by delta Z is equal to minus Riz minus L delta I by delta T, minus delta I by delta T is equal to minus Vz minus C delta V by delta T. So in the phasor form we can write dVz by dZ is equal to minus R plus j omega L into Iz, or you can say we can convert this into the, we can take the Laplace transform of this equation 1 and equation 2. So when we'll take the Laplace transform of this, it will become diz by dz is equal to minus G plus j omega C into Vz. Basically this is the function of t and this is the function of z and t. Both I and z are the function of t. Here we can write here, if I take the Laplace transform of this, then we will get these two equations. So how will you find this propagation constant as well as the characteristic impedance? So after solving these two equations, we will get that the propagation constant is under root R plus j omega L G plus j omega C. We can write here propagation constant is nothing but the summation of alpha and alpha, nothing but alpha plus j beta, where alpha is the attenuation constant and beta is the propagation constant. Alpha is the attenuation constant and beta is the propagation constant. And what is the characteristic impedance? After solving this equation, we will get the characteristic impedance Z0 is equal to R under root R plus j omega L upon G plus j omega C. This is nothing but R plus jx. We can convert this. So these are known as gamma and Z0. Propagation constant and characteristic impedance is known as secondary constant of the transmission line. And for lossless line, the gamma is imaginary and Z0 is real. This is the calculation of the propagation constant for R is less than j omega L and R is less than omega L and G is less than omega C. You can see here we can neglect. I have considered here R is less than omega L and G is less than omega C. So this will be equal to under root j omega square LC, and you will get here 1 plus R by j omega L, 1 plus j by omega C. So after calculation, I will get here j omega under root LC 1 plus this after expanding using the binomial expression. So I will get here 1 by 2 R under root C by L plus G under root L by C plus j omega under root L by C. So I can compare here, gamma is equal to, I have already written there, gamma is nothing but alpha plus j beta. So real part will give the value of alpha and imaginary part will give the value of beta. So What will be the value of alpha? Alpha will be equal to the 1 by 2 r under root c by l plus g under root l by c. This is the value of alpha and this is the value of beta. So beta will be equal to omega under root lc. Similarly, we can calculate the characteristic impedance Z naught is equal to r plus j omega l upon under root r plus j omega l upon g plus j omega c. So I have considered here r is less than omega l and g is less than omega c. So we can ignore this value, or after expanding this up to the first term, I will get here under root L by C 1 plus 1 by 2 R by j omega L 1 minus 1 by 2 g omega C. So after calculation I will get here this can be ignored and this can be ignored. So I will get here under root L by C. So for lossless transmission line, Z naught is real. Z naught is equal to under root L by C. So this is the numerical related to this transmission line. We can easily find the value of characteristic impedance and the propagation constant using the formula. Gamma is equal to under root r plus j omega l and g plus j omega c, and Z naught is equal to r plus j omega under root r plus j omega l upon g plus j omega c. So here the transmission line terminated with the load in perfectly matched condition and in mismatched condition. Z naught is equal to ZL is known as perfectly matched condition, and Z naught is not equal to ZL is considered as the mismatched condition. So in case of perfectly matched condition, maximum power will be transferred to the load, and there will be no reflected wave inside the transmission line. And in case of mismatched condition, mismatched transmission line, there will be reflected wave in the transmission line and there will be standing wave pattern. So VSWR will be the finite value. Similarly, we can calculate the value of voltage and current for the infinite length. So in case of infinite length, I will get here, this is the solution of the equation, voltage and current equation. Vz is equal to V naught e ki power minus gamma z and is equal to V naught plus e ki power minus g beta z. So here I can calculate the characteristic impedance by using simple formula. Voltage by current is equal to the impedance. So, and if the characteristic, if the transmission line is terminated with the load resistance, then what will be happen? This equation will change. So Vz will be equal to V naught plus e ki power minus j beta z and plus V naught minus e ki power j beta z. And similarly, we can write the solution equation for the current, and we can find the characteristic impedance. But in case this characteristic impedance will not be same as at Z is equal to 0 and at Z is equal to L. So both the values will be different. So what will be the deflection coefficient? Reflection coefficient is nothing but V naught minus upon V naught plus. We can calculate by using the voltage and current equation. We can find the value of reflection coefficient by using the solution of the voltage and current. So what will be the value of this reflection coefficient? Reflection coefficient is nothing but ZL minus Z naught upon ZL plus Z naught. And we can also find the gamma at any arbitrary point. So gamma, that is reflection coefficient, is the function of L, and this will be the value of the function of L, that is gamma minus L is equal to gamma 0 e ki power minus j 2 beta L. Similarly, we can find the transmission coefficient. So for finding the transmission coefficient, we can easily calculate using the solution equation of the voltage and current. So the voltage standing wave ratio is used to measure of how flat the line is, and the VSWR is independent, and it is clear that the VSWR is independent of the position of the line. So VSWR is nothing but 1 plus rho upon 1 minus rho, that is where rho is the reflection coefficient. Now we can calculate the power flow. Power flow is nothing but the P average is equal to real part 1 by 2 real part of the Vz into Iz. So by using this formula where we can put the value and we will get P average is equal to 1 by 2 V naught square upon Z naught 1 minus gamma Z square, where P naught 1 by 2 V naught square upon Z naught is nothing but the incident power, and this equation can be rewritten as, if I multiply this incident power to this reflection coefficient, I will get the reflected power. So this is nothing but, this P average is nothing but the incident power minus reflected power. Now what is the waveguide? So this waveguide is nothing but the structure. This is the structure based on the single conductor used for the guided propagation of the EM waves, and this waveguide propagation and the wave propagation inside the waveguide takes place through multiple reflection and to avoid the losses during these reflections. So waveguide should be totally internally reflected. So waveguide acts as the high pass filter and therefore propagation takes place above the cutoff frequency. The cutoff frequency represents the lowest frequency of operation below which the propagation takes place. So F naught, if F naught is greater than Fc and lambda naught is less than lambda c in case of waveguide. So what is the evanescent mode and dominant mode? So F naught is less than Fc and lambda naught is greater than lambda c, then wave propagation will not take place, and modes corresponding to this are known as evanescent modes. And dominant, what is the dominant mode? A large number of waves or larger number of modes can propagate inside a waveguide depending upon the frequency of operation. So if F naught is equal to Fc, then this is known as dominant mode, and F naught is greater than Fc, then it's known as higher mode. So what is the solution of this reflected wave? So as I have already told you that this electric and magnetic waves are represented by these two equations, and where gamma is the propagation constant and gamma is given by j omega under root j omega mu sigma plus j omega epsilon, and this gamma is nothing but alpha plus j beta. Now we have to find the components of this E and H which will satisfy this complex scalar wave equation, that is Helmholtz equation, and this equation is del square psi is equal to gamma square psi, and in rectangular coordinate we can write del square psi upon del x square plus del square psi upon del y square plus del square psi upon del z square is equal to gamma square psi. Now what will be the solution of this equation? By using the variable separation method, we will consider here gamma psi is equal to x, y, z, where x is the function of x, y is the function of y, and z is the function of z. Or you can say xx is a function of the x coordinate only, and yy is a function of y coordinate only, and z is a function of z coordinate only. By using this equation 5, so I will substitute this value in the equation 5. Substitute the equation 5 to equation 4. I will get here 1 by x d square x by dx square plus 1 by y d square y by dy square plus 1 by z dz square by dz square is equal to d square z by dz square is equal to gamma square. This is nothing but minus kx square minus ky square minus kz square is equal to gamma square. So I have replaced this d square x by dx square by k square x into x. D square y by dy square is equal to ky square into y. D square z by dz square is equal to minus k square z by z. So this is the solution of the this is the solution of the equation 4. And now how can we find the value of x, y, and z? So I have to use x is equal to a sin x plus b cos xx. Y is equal to c sin s. So we have to find here CF and PI. After finding the value of CF and PI, we will get the value of x, y, and z like this. and the Helmholtz equation will become psi is equal to A sine, Helmholtz equation or the solution of Helmholtz equation will be A sine kxx plus B cos kxx, C sine kxyy plus D sine kyy, E sine kzz plus F cos kzz. So this is the solution of Helmholtz equation. Now how will you find the propagation constant in this case? So for finding the propagation constant, I will use I will assume that the wave propagating in z direction. So the gamma z square will be equal to gamma square plus kx square plus ky square, that will be equal to gamma square plus kc square, where kc is the cutoff wave number. Kc is nothing but Kc is equal to under root kx square plus ky square, and for lossless dielectric I will consider here gamma square is equal to minus omega square mu epsilon, and then gamma z will be equal to gamma g is equal to plus minus omega square mu epsilon minus Kc square. So these are the cases where I will consider for the propagation constant. In case 1, there will be no propagation, that is gamma z is equal to 0. So this is the Evanscent mode, and Fc will be equal to 2 pi 1 upon 2 pi under root mu epsilon under root kx square plus ky square. In case 2, there will be the propagation in the waveguide if omega square mu epsilon is greater than Kc square. In that case, gamma z will be equal to plus minus j beta z. So here the value of gamma z will be plus minus omega under root mu epsilon under root 1 minus fc upon f chi square. In case 3, the wave will be attenuated if omega square mu epsilon is less than Kc square. So gamma g is equal to plus minus alpha g, and this will be equal to this. So therefore the solution of Helmholtz equation in rectangular coordinates is given by this: gamma is equal to sine xx plus this and this, e की power minus j beta z. So this is the solution of Helmholtz equation. And next is the types of modes. So in case of waveguides, we are using the two modes, T mode and TM mode. In T mode, this T mode is also known as H wave and characterized by the fact that the electric vector being always perpendicular to the direction of propagation, and in T wave only the E field is purely transverse to the direction of propagation and the magnetic field is not purely transverse. In case of TM mode, transverse magnetic mode is also known as E wave, that is characterized by the fact that the magnetic vector H is always perpendicular to the direction of propagation. In T wave, only the H field is purely transverse to the direction of propagation and the electric field is purely transverse. That is, Ez is not equal to 0 and Hz is equal to 0. So this is all about the waveguide, short and crisp. And similarly, I have already discussed the transmission line. So some part I have discussed in this lecture also. So this is all about the waveguide. Thank you.